Hello all, I am Samit Thosar and today I am going to talk about convolutional neural networks or CNN or ConNets. I am going to follow the following flowchart throughout this video. Firstly, I am going to introduce the CNNs and their applications. Then I am going to talk about the architecture of the CNNs and the block diagram. We will then see how to convert an image into a matrix. Then we will get to the crux of the convolutional neural network, that is the convolutional layer. The CNN convolutional layer consists of the following four parts, that is the filtering, padding, stride, and depth. I'm going to explain all these aspects in detail in the later part of the video. After that, I'm going to show how to convert the RGB image into like how to convolve an RGB image. So its RGB image is basically a colored image. Then, as you know, most of the applications in this real world, are nonlinear in nature. So we need to incorporate certain nonlinearities in our CNN. I'm going to talk about ReLU nonlinearity. After that, we are going to talk about pooling. Pooling is basically done to decrease the computational time. Then we are going to talk about the fully connected layer. And FCL is basically combining the basic neural network to our convolutional neural network for the purpose of classification. Then I'm going to run you through the entire training process with all the steps. Lastly, I'm going to talk about all the other convolutional neural networks architecture that are already being designed in this world. ConNet are a type of neural network which are effective in areas like classification and recognition of images. CNNs have also been successful in identifying faces, objects, traffic signs, apart from their general use in self-driving cars. CNNs make an explicit assumption that inputs are images, which allows us to encode certain properties into their architecture. These then make the forward function more efficient to implement and vastly reduce the amount of parameters in the network. As you can see from the image, a soccer player is playing with a ball. We know this, but how does our network know? It seems like magic, but it's all just a code. Our CNN is trained rigorously and thus gives us the correct caption. CNN are also being used in natural language processing. The purpose of this video is to explain how CNN works with images. ConNet architecture. Just by taking a glance at this right hand side over here, you can see there are four classes: the dog class, the cat class, the boat class, and the bird class. There are numbers written right besides it. These numbers are basically the probabilities that the particular image belongs to this particular class. So as you can see, this image here is of a boat, and CNN predicts this image to be a boat 94% of the time. That means the prediction of the CNN is perfectly correct. By looking at this huge block diagram, you may feel it is really complicated. I mean, it does look really complicated. However, we can break it down into small subsections to get a better understanding about this architecture. These subsections are basically the building blocks of every CNN. These building blocks are the convolution layer, the nonlinearity, pooling, and the FCL. We are going to talk about all these blocks in detail. Understanding how these work is an important step to developing sound understanding of the CNN. Image as a matrix. You may have this big question. How can an image be taken as an input to a network? How do we code such a thing? Essentially, every image can be represented as a matrix of pixel values. As you can see here, this is basically an image of an 8. It is taken from the handwritten digit dataset. This image can be converted into this matrix. You can see that there are certain numbers written over here. These numbers can be easily fed into any neural network. You can also see that the numbers that are of a greater value, like this 253, this 242, and all the other higher value numbers, coincidentally form the shape of an 8 that was already there. This just states one fact that as you go from 0 further away from 0, these black images are denoted as a higher value, whereas the white spots are denoted by a lower value. This image is also called a grayscale image. This is so because there are only two colors like black and white. An RGB image, which is a colored image, has three channels, namely red, green, and blue. The also another fact is that the pixel values inside this matrices has to be between 0 and 255. It cannot be greater than 255. Also, the matrix here is a two-dimensional matrix, so it is an m by n matrix. Here, this L defines the channel number of channels that are present. As already mentioned, for an RGB image, the number of channels is equal to 3, and for a grayscale image, the number of channels is equal to 1. There is a small mistake over here. 0 indicates white and 255 indicates black. Sorry for the confusion. We will now be starting the first building block of the CNN architecture, that is the convolution block or the convolution layer. The convolution layer is the core building block of the CNN. This block does most of the heavy lifting. The purpose of the convolution layer is to extract features from the input image. This is the input image. It consists of zeros and ones. Ideally, this can be any number between 0 to 255. These zeros and ones are just taken for mathematical simplicity. The convolution layer also preserves the spatial relationship between the pixels. This is because it learns features using the small squares of the input data. So at a time, only this much of the input data is used to extract the features. Uh, Convolution of the input image with this filter matrix. Now this is a filter matrix which is also denoted as kernel in many textbooks and research papers. This filter matrix can also be found using different parameters, like we can just assume these 9 units to be just w1, w2, till w9, and find these parameter values while backpropagating. However, we can also assign certain values that we know to use this as a filter matrix. This here is the feature map that is found by convolving the input image with the filter matrix. Feature map is basically the extracted features that we want to find. We will now go into the first part of convolution, which is the filter part. As you can see in the previous image, we had a 5 by 5 matrix, which was our input image, and we had a kernel whose values are as shown, which is 101, 010, 101, and then we get the feature map. Now I will show you how to obtain this feature map from this convolution, that is how to do the convolution. So we take the filter matrix and impose that filter matrix on our input image. So you can see this occurish thing here, and here it is written 1 1 0 1 0 1 0 1 0 1, right? So how do we get this 4 from this calculation? So what we do is we multiply 1 by 1, which is this term, then 1 by 0, which is 0, then 1 by 1, which is again 1. This part will give you a 0. This will also give you a 0. This will also give you a 0. And this will give you a 1. This will give you a 1. And finally, this is a 0. So in all we have 4 ones. This, and this. We add those all up and we get a value of 4. That's how we get it over here. I will show you a video of how all the other computations are being done over here. Sorry for the confusion. So as you can see, the next part will give you a 3, then a 4, then a 2, 4, 3, 2, 3, 4. And that's how we get our feature map. Now I will tell you about how do we get this size of a 3 by 3. Like, will it always be a 3 by 3, or does the feature map size also change? So the feature map size actually depends on the size of your input image and the size of the filter. We have the size of our input image as a 5 by 5 matrix, which can be denoted as an n by n matrix. Our filter is a 3 by 3, which can be written as a f by f matrix. So the size of the feature image is actually just given by a simple formula, which is n minus f plus 1 by n minus f plus 1. If we put our values over here, so we have n is equal to 5, so it is 5 minus f, which is 3, plus 1, which gives us the value 3. Similarly, for the next dimension, it comes out to be 3, so we get a 3 by 3 feature matrix. I will now show you a real world example of the filter. So we are going to do vertical edge detection. So in vertical edge detection, we have our input image given to us as a 6 by 6 matrix, which is this, which has 3 columns of tens, which are positive numbers, and 3 columns of zeros, which are just zeros. So in our case, the positive numbers are going to be denoted as white for positive, black will be denoted as negative, and gray are just zeros. So here you can see that there are 3 columns of 10 and 3 columns of 0. So we have a white and a gray image, which gives us this edge right over here, like this. We have a kernel, which is a filter matrix, which has 3 ones in the first column, then 3 zeros in the second column, and then 3 negative ones in the third column, which gives us a white, gray, and black image as shown over here. When we do the convolution and apply the steps that were shown in previously, you will get this 0 from here. So you get 10 into 1, 10, So this is into 1, 1, 1, and this is minus 1, minus 1, minus 1. So you add up all these tens, we get 30. These are all negative 30, and these are just zeros. So we add it up and we get a 0 over here. Now this 30 is found from over here. Sorry. So we just have a 1, 1, 1. So this is 30. 0, 0, 0, which is 0. We have a minus 1, minus 1, minus 1, and all these are 0, so those are also 0. So we get a 30 over here. Now solving all these 16 boxes, we get our feature map as shown over here. It has a gray, a white, and then a gray again. So you can see there is this edge which is in the center and this edge which is in the center. So we are basically detecting this edge right over here. Now you may feel that this edge is basically very small in its width, while this edge has a thick, like its width is very high. This may cause a few problems in a small image like this, which is a 6 by 6 image. However, if we have a 100 by 100 image, this edge won't really cause much of an issue. We'll now move to the next part of convolution, that is padding. There are two downsides to the filtering process. The first one is that the image shrinks due to multiple convolutions. We have our input image and the filter image, and we take the convolution of it to get a feature map. This is just the first convolution. Now, if we do the convolution of this feature map again with the same filter matrix, we will get a 1 by 1 image. A 1 by 1 image is very small and is very difficult to handle. This will create certain problems. The other drawback is that the information at the edge, like this or this, only are given less importance. This is because this part is only taken into consideration in this block. Whereas the one in the center is given higher importance because it comes into many squares. These are very important drawbacks. To avoid these drawbacks, we do padding. What is padding exactly? Basically, we have our block, that is our input image, and we pad that image around the corners. This is basically adding one border to an image, or we can add multiple borders to an image. So say if we have a 5 by 5 image, when we add a border, our input image becomes a 6 by 6 image. The size of the filter remains the same. The size of the feature map though will change. The formula for the size of the feature map is given as this, which is n plus 2p minus f plus 1 by n plus 2p minus f plus 1. In our case, n is equal to 5, p, that is the amount of padding, is equal to 1, since we are adding just one amount of padding on the side, and we have f is equal to 3. So applying the formula, we get 5 plus 2 minus 3 plus 1, which is equal to 5.
So the size of our feature map will be 5. If we pad the value of 2, that is 2 borders, then this becomes 4, and then the size of the feature map is 7. Now there are various types of padding. So in general there are two common choices. The first one is a valid padding, that is just the no padding thing. So we just take the input image and do what we have already previously learned in the filtering stage. The second one though is the same padding. Now what does same padding do? You can see here it's a 5 by 5 image, and we get a feature map of 3 by 3. What we do is, if we pad the image in such a way that after filtering we get a 5 by 5 feature map. So basically we want our n plus 2p minus f plus 1, which is this formula, which is the size of the feature map, to be equal to the size of the original image, which is equal to n. Just doing simple algebra, n gets cancelled, we get 2p minus f plus 1 is equal to 0, we get 2p minus f is equal to minus 1, and then we can do 2p is equal to f minus 1, and p then becomes f minus 1 by 2. Now this f is usually odd, so p is usually an integer. You won't find f to be even much often. It's generally odd. In our case, we have a 5 by 5 input image, a 3 by 3 filter. So just applying the formula, we get it p is equal to 3 minus 1 by 2, which is equal to 1. Now, this is the general scenario. To specify what the padding is, we can either specify just the value of p, that we can say that p is equal to 2 or p is equal to 3, whatever we want. Or we can just say that it is a valid convolution, which means that it doesn't have any padding, and just continue the process as we normally would do. And the third one is that we can say it's a same convolution, that is we pad the image is in such a way that the feature size, the size of the feature map remains the same as the original input size. Up until now we have been talking about grayscale images, which are just 2D images like a 6 by 6 matrix, and then those are just called grayscale images. Now we will discuss about an RGB image, which is a colorful image which has 3 channels, that is red, green and blue channel. The 6 here is the height, this is the width, and this is the channel, that is the number of channels. Similarly, for our filter, we have a height, a width and number of channels. The important thing is that the number of channels in the input image must be equal to the number of channels in the filter matrix. As you can see over here, we have a 3D image, which is our input. We have a 3D filter, but our output is just a 4 by 4 matrix, which is just one channel. How does this happen? We do the convolution of an RGB image in a similar way to a grayscale image, just that instead of moving a box like a square, we move a cube. So this 3 by 3 by 3 is, you can take it like this, a basic cube, and just place that cube over here like this. So over here you have a cube, then there are total 27 values, 1 2 3 4 5 6 7 8 9 and 9 other two times. So this is for the red channel, this is for the green channel, and this is for the blue channel. These 9 are to be multiplied with the corresponding 9 points, and then we just add them up to get a one number. We do the next step by sliding the box towards one step towards the right, and we again get a number over here. We do the same thing continuously for the entire input image. Now, how to do vertical edge detection in this? So if we just want to detect the vertical edges in the red channel, then we can choose the filter matrix of this to be 1 1 1 0 0 0 minus 1 minus 1 minus 1 for the red channel. For the blue channel, we can take it as just zeros, and similarly for the green channel, we can take it as all zeros. So what will happen over here is that the feature map we will get will be a vertical edge detected map of just the red channel. But what if we don't care about any particular channel? We just care about the vertical edges, whether it be red, green, blue. Then we will use this same filter for the blue one and the green one as well. That's how we can do convolution of a RGB image using a filter. So we have finally finished the convolution part of the CNN. Now we will move on to the non-linearity aspect of it. There, as you can see in the block diagram, there is a additional operation called the ReLU operation, which is the rectified linear unit operation that has been performed in every convolution operation. So what exactly does a ReLU do? So ReLU performs an element-wise operation. So if you have a block diagram, an image after feature map as something like this, which is minus 1 1 1 0 0 0 2 3 minus 3, something like this, then a ReLU will do an element wise operation on this and convert this image into something like this, where this becomes 0 1 1 0 0 0 2 3 0. So what it does is it takes the negative pixels and replaces them by 0. So basically the output of the ReLU you can say is the maximum of the 0 and the input. So if the input is greater than 0, then the output is input. If the input is less than 0, then the output is given as 0. So as you can see from this graph, you will just see a straight line over the positive axis, while for the negative axis it just remains as 0. Why do we need this ReLU thing to happen? So in most applications that is a real world application, the data is non-linear in nature, and our convolution is an element wise multiplication, that is a matrix multiplication. So it is basically a linear operation. There is no non-linearity aspect present in the convolution part. So to incorporate a non-linearity in our CNN, we need to introduce a certain non-linearity, and that non-linearity is introduced by ReLU. We can also use other nonlinear functions like tan h or sigmoid function, but it has been found that ReLU has performed better. You can see from this image over here, there is the black portion of over here, over this image on the left hand side has been replaced by a grayscale gray image, where the white portions remain as it is. It just again amplifies the point of how a ReLU works. Like the black which is negative, has been removed from the rectified feature map. You can see from the block diagram that after the convolution layer and the ReLU operation, we will move on towards the pooling layer. So what does the pooling layer do and why it is necessary? So a pooling layer is necessary to speed up the convolution process. The convolution process is pretty slow because it is doing element wise multiplication all the time, and for a long for a very huge image it will take a lot of time. So we will use pooling, and pooling is also done to increase the robustness of our system. And how is it basically done? So if we have a 4 by 4 matrix that is given over here in this figure, we divide this figure into 4 parts. So a red part, a green part, a yellow, and a blue. So we just take the red part and we find out what is the maximum pixel value in this red part. As you can see, the maximum pixel value is 6. Then we put this 6 right over here. We take the green part, take its maximum value, which is 8, and then put it over here. Similarly for the yellow one and the blue one, and we get our feature map, rectified feature map after pooling. What you can say is that pooling is basically just filtering with a filter of size 2 and stride 2. So it will take 2 positions from here and then 2 positions down and then again 2 positions to the right. That's how it will work. So we have the parameters f and s, which are also called as hyperparameters. Once set, they are fixed. They are basically so they are the parameters that cannot be learned. But once you have set it, they are as it is, and you cannot change it in either way or form. So we do not consider pooling layer and convolution layer as a separate layer, but it is sometimes or many times have been considered as a single layer. So convolution, nonlinearity, and pooling forms one layer in our CNN architecture. This, however, what I have shown you right now is max pooling. Similar to max pooling, we can also do an average pooling. So average pooling is basically we take the average of all the pixel values inside this box and then write it down over here. We round it down. So here it is 6 plus 5, 11 plus 2, that's 13, and divided by, so we take the average of it, like 13 by 4, so it's around 3 point something, so we write it as 3 over here. Another thing over here is this is just a grayscale image, and it has just one channel. What if there are multiple channels? So what if we have another channel over here like this? How will the pooling look? So for such an image, the pooling will be like this. We'll have another pooling, another feature map behind stacked behind this original feature map, and the values inside that feature map will just be the maximum or the average value, whatever we choose inside these values inside this image. So if this image also will have 16 values, we can have divided into 4 segments like this one and then do it. Another important thing is that the number of channels like this. So this has 2 channels, and this also will have 2 channels. So if the number of channels are 3 in this image, then the rectified feature map will also have 3 channels. In any case, the number of channels should remain the same. It has also been found out in practice that max pooling in general works better than average pooling. So we will mostly use max pooling. Now, what are the basic advantages of pooling? Is that it makes the input representation smaller and it reduces the number of computations that are required. from the rectified feature map we found in the previous non-linearity function, which is this only non-negative map. We do pooling and we get a maximum and a sum pooling graph. So far we have seen how convolution, ReLU and pooling work. It is important to understand that these layers are the basic building blocks of any CNN. The output of the pooling layer acts as an input to the fully connected layer. Fully connected layer is a traditional multi-layer perceptron that uses a softmax activation function at the output layer. The term fully connected implies that every neuron in the previous layer is connected to every neuron in the next layer. So here if we have certain neurons, suppose these many, then fully connected means that every neuron from the previous layer is connected to every neuron in the next layer. Assume after pooling we have a 4 by 4 by 2 matrix, so that's total 32 units. We flatten this matrix into a 32 by 1 vector, and those gives us our 32 neurons. We add a hidden layer of say suppose 10 units. Okay, and suppose if we have like 3 or 4 outputs, in the port example we will have 4 outputs. So a fully connected layer will connect all the neurons in this layer to all the neurons in this layer, and then all the neurons from the hidden layer will be connected to all the neurons in the output layer. The output layer will give us the probability of the input image lying into what kind of class. When we connect the input layer, hidden layer and the output layers, it just becomes a standard neural network which has a certain weight matrix and a certain amount of biases and outputs. The purpose of the fully connected layer is to use the features for classifying the input images into various classes. Apart from classification, adding a fully connected layer is also a cheap way of learning non-linear combinations of these features. Most of the features that are extracted from the convolutional and pooling layer may be good for a classification task, but a combination of these features may even be better. Also, on a interesting on a fact is that the sum of the probabilities at the output is always equal to 1. This is ensured because of the softmax whose activation function works in such a way that the outputs are squashed into a vector between 0 to 1. So we have finished with the block diagram. Now we have done all the basic building blocks and have understood what are their significance and how do they work. Now we will see how does the entire training process put together works. We also know that the convolution and the pooling layers along with the ReLU act as feature extractors from the input image. The fully connected layer acts like a classification layer. So we will have classification at the output layer. Um, Now I will be explaining the entire training process. We have the input image as boat and we have decided our target vector to be 0 0 1 0 because our third class is the boat and we want to detect this boat accurately. So how does this work? So in step 1 we will initialize all the filters and parameters and weights with random values. So the filters that are present in the convolution layer, that I said earlier, that can be any weight matrix like W1, W2. We can take any random initialize it as anything, and then in the back propagation method they get readjusted. So that's how we will just randomize the weights and parameters. In the next step, the network takes the training image as the input and it goes through the forward propagation step. So what exactly is the forward propagation step? The forward propagation step is basically the input image goes from the convolution layer through the polling layer, then it will go through the another convolution layer, another polling layer, and then finally go into the fully connected layer. And we will find out the probabilities of each class. So let's say the output probabilities for the both image uh, that we have are something like this: 0 0.2, 0 0.4, 0 0.1 and 0 0.3. These are just the uh, first predicted values of the image. So it's not really the final output, it's just the first stage. What we will do is, after getting this vector, we will calculate the total error that is present, and the total error is basically given by this formula, which is the summation of half of target probability minus the output probability square. So we have the target probability as 0, 0, 1, 0, and we'll just subtract it with and then square and find out the error. In the next step, we will use back propagation to calculate the gradients of this error with respect to all the weights in the network. So there are weights on each of the branches present in the neural network. So basically we have something like this, and once we connect our previous layer to the next layer, these values are the weighted values. So these values will change according to the error. When the same image is input again, output probabilities might now be a bit different. Let's say like something very close to what we want. So like 0 0.1, 0 0.1, 0 0.70. This basically means that the network has learned to classify this particular image correctly by adjusting its weights, uh, because the output error has reduced. The parameters like the number of filters, filter sizes, and all have to be fixed before step 1, and they do not change during the training process. Only the values of the filter matrix and the connected weights can get updated. This is a very important point that needs to be understood. So we have found out that our network is learning, but it has not yet reached that state. So what we will do is we will repeat the steps from step 2 to step 4 continuously till we get a output which is very close to our target output of 0, 0, 1, 0. As you can see from the first image that I had shown you over here, we get certain probability, and at 0.94 we will stop. So it is like 94% we have detected it correctly. So again, to summarize, what we will do is we'll first set the filters randomly and the weights randomly. Then we'll pass the image through the entire process and we'll find out the probabilities, calculate the error, backward propagate it through the entire network, update its weights, calculate the probabilities again, calculate the error, and we will do this process again and again till we get the error to be very small. The last topic of this convolutional neural network video that I will be covering is the available convolutional neural network architectures. The first architecture is Linnet architecture, which was developed in 1990s. This architecture is basically what we have been discussing throughout this video. Then the next architecture is AlexNet architecture, which was developed in 2012. Uh, AlexNet was a deeper and a much wider version of Linnet, and it was a significant breakthrough with respect to the previous approaches in CNN. After that came ZFNet, which was developed in 2013, which was a winner at a convolutional neural network competition. Um, it was also an improvement over AlexNet by tweaking the architecture parameters. In 2014, Google came with the GoogleNet convolutional neural network architecture. Its main contribution was the development of an inception module that dramatically reduced the number of parameters in the network. With like GoogleNet has like around 4 million parameters compared to AlexNet, which has around 60 million parameters. In 2014, VGGNet came into existence. Its main contribution was showing that the depth of the network is a critical component for good performance. Then came ResNets in 2015, also known as residual networks. Uh, ResNets are currently by far the state-of-art CNN models available. Uh, in 2016, recently, DenseNet came into existence. Uh, DenseNet has shown to obtain significant improvements over previous architectures like GoogleNet and ResNet. And that's it for the video. I'm now going to talk a little bit about AlexNet, which was designed in 2012. This is the architecture of AlexNet, and this architecture will use all the properties and the kernels, filters, stride, and everything that we have learned in this video in this architecture. So we have a 227 by 227 by 3 image. We take a kernel of size 11 by 3 whose stride is 4, and we take 96 of such kernels. So we apply the formula of n minus f by s plus 1 to get the size of our feature map. So we do 227 minus 11 by 4 plus 1, which gives you 55. So a 55 by 55 matrix. And then we have 96 such filters. So we get this 96 depth. Then we do a max pooling, which is a 3 by 3 kernel, and we are going to use stride is equal to 2. So again, applying the same formula, we get our feature map size to be 27, and therefore we get a 27 by 27 dimension of our feature map. As you all know, when we apply max pooling, the depth does not change. So this here remains 96. So after max pooling, we will again do the convolution, but this time we will decrease the size of our filter. So instead of the 11 by 11 that we had used earlier, we will use a 5 by 5 kernel, and we will use 256 such kernels. We will also do a padding of 2. This is done just to keep the size of the feature map same as the size of the input. So we'll again apply the formula, which is 27 plus 2 into 2 minus 5 by 1 plus 1. So that's just n plus 2p minus f by s plus 1. So we get it is equal to 27. So we get a height and the width as 27 by 27. And we are using 256 such kernels, which will give us the depth of the image. We will then do the max pooling again. This time we will take the same filter which we had previously used, which was of size 3 by 3 and stride equal to 2. We by applying the formula, we get the size to be 13, so we get a 13 by 13. Again, the depth does not change when we do pooling, so this becomes a 256 depth. After that, we will decrease the filter size for the convolution again. So here now we will use a 3 by 3 filter. We want to have same padding, so we do padding of 1, and we use 384 kernels. So we'll get this as our output. We don't do further max pooling immediately as we have done previously, like a convolution pooling. Now we will do 3 convolutions together. This one was the first, this one was the second, and this one was the third. Then we do the fourth one again, which gives us a 13 by 13 by 256 matrix. This 256 comes because of these 256 kernels. Then we will do a max pooling again to get us this 6 by 6 by 256 feature map. Now 6 by 6 by 256 is basically 6 into 6 into 256. Now what we learned in our FCL part, we take the multiplication of these and convert it into a row vector or a column vector. So this 6 into 6 into 256 gives us a 9216 vector, 9216 units, and we can use those units like neurons. Then we'll add 2 hidden layers which are fully connected, and we will use the softmax activation that we had learned with 1000 neurons. 1000 this is basically our output. So we have total 1000 classes, so we have 1000 outputs. That's it for AlexNet. The next architecture that I'm going to talk about is the Inception module. So this is a part of Google Lenet. So Inception network has 4 versions till now: V1, V2, V3, V4. I'm going to talk about the crux of these versions, which is the Inception module. So here the main criteria or the main stumbling block that we used to encounter is that we don't know what type of filter we have to use, whether we have to do the 3 by 3 convolution or a 5 by 5 or an 11 by 11. In AlexNet we use all 3 of them, but in Inception module it doesn't matter which convolution we are using, so we can just use the 1 by 1 convolution, 3 by 3 convolution, 5 by 5 convolution, and a 3 by 3 max pooling, and concatenate it together to get a filter concatenation. Let us now assume that the previous layer's image dimensions of the feature map is given by this dimension, that is 28 by 28 by 192. Let us assume that the total number of filters in 1 by 1 convolutions are 64. In 3 by 3 convolution are 128. For 5 by 5 convolution I will be using say 32 filters. And for max pooling the stride should be equal to 1, and I'm using same padding. The padding for all the convolutions is also same. So what will be the convolution of this filter, 1 by 1 filter, with the previous layer? So it will just be 28 by 28, since we are using same padding, of course. And then the depth is equal to the number of filters that we use, so that will be equal to 64. For 3 by 3 convolutions we can use the same logic, same padding, so 28 by 28 by 128. For 5 by 5 convolutions, same logic, same thing we are going to do. So it's 28 by 28 by the number of filters, and over here it is going to be same padding, so 28 by 28, but the depth is going to remain the same as the previous layer since we are doing pooling. Now what we do is we concatenate all these outputs over here, so this plus this plus this plus this, that is the total 4 outputs we are going to concatenate. So the final image feature map we are going to get will have the size 28 by 28 by the addition of this, 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 and this. So that comes out to be 416. So this is how we can use the inception module, and then that's the end of this video. Just the references are remaining. So these are the references. uh, these are the blogs that I have taken the information from and the images from, and they own these images and the video. So I do not own anything. You should check out these two amazing blogs. They have a lot of information about CNN, and you can find them very helpful. You can also join the course by Andrew and G on Coursera. Amazing course. I highly recommend it. If you are interested in deep learning, you should be taking this course. It's very insightful and helpful. Thank you for your patience.